viewers, maybe outside of Pali. This is our Pali Impact Project. We are doing today a podcast. Topic number 1, Big Bang. Let's get right into it. Kablam. All right, I'm Alexander. Who are you?
I'm Nicola Rafael Defendicho.
I'm Isaac Kirby.
Didn't know we were doing like last name, middle name, all that.
Oh, this is the real deal.
Right, real deal.
But yeah.
All right, so how should we start it off? So you want me to you want to go like chronologically, walk through the Big Bang?
Well, I think the beginning of the universe is everything's like chronological. It matters a lot, the time that it goes down.
Right,
so I think we just started from the beginning, of the Big Bang.
You're right.
What really just went down?
Well, so the first kind of area, the first sector we're going to want to talk about is the radiation era. And all of this, you kind of have to take into a perspective. It really happened from, from 10 to the negative 50 seconds, and then it was like, it's all less than a second. And here's also another big theme.
So you're telling me this stuff's happening like that?
Yeah, but
it's like instant?
Before you can even get your fingers ready for the snap, each thing is like a little slide down. But a big theme is the temperature. It's super hot at the begining, and it's kind of as things cool down, that's when different new building blocks of matter are able to form. So the first epoch I want to talk about is the Planck epoch, and Planck is actually like a unit of scale. So everything was at Planck length, which is really tiny.
Is that similar to the Planck's constant, or is that?
I think that's probably has a relation. I'm not actually sure what that is there, but it is. Everything was very small and is kind of like quantum physics type size things. So they had the 4 super forces, which are gravity, strong nuclear, weak force, and EM radiation. And at this point in this epoch, basically no time has passed. It's 10 to the negative 44 to the power of negative 44 seconds. So it's like 0.0044 zeros like that. And so all the 4 super forces, they hadn't broken off. It was just one unified force. And to be honest, scientists don't really know a lot about what happened here. But I mean, who knows if there is a lot to know? We don't know. I mean, that's why scientists don't know. And then following that, there was the grandification epoch. So it cools just enough. So remember that one unified force I was talking about. Gravity here is actually able to peel off, and it separates. And then so there's strong nuclear, weak, and EM. And that made electronuclear force. So that was a big force of that epoch. And the first elementary particles form. So those are the first particles, simplest forms of matter possible, not even a substructure, but they will be the building blocks of protons and neutrons, electrons, and more. So building blocks of quantum physics, I guess. 2 of these, like an example of 2 of these particles, I got here in the notes, fermions and bosons. Here we're getting pretty complicated, but I can read a little gig on bosons maybe. These are the 5 force carrier particles mediate the interactions between weak magnetic, strong magnetic, and electromagnetic forces, and they are the fundamental reason for the attractions and reactions we view as forces. So these tiny little particles, these bosons, are like, and during this grandification epoch, are a huge contributor of the forces we have today. So it's pretty insane how that all worked out. And then the next epoch was very important, the inflationary epoch. So just to put this into perspective, this was from 10 to the negative 36 seconds to 10 to the negative 32 seconds. But at this time, like, it's hard to describe it, but I mean, what is that to the universe? That was like everything in the universe. They couldn't compare it to all the time that's passed today. But the universe grew from the size of about an atom to about a grapefruit. So that was the massive inflation. And the strong nuclear force now broke off that of that unified force, and it broke off from weak nuclear and EM forces. Temperature dropped. That was also like keeping with that theme. That's what allowed it to happen.
So you were talking about, as the universe is expanding, like you said, from the marble or atom to grapefruit, right? So that's happening because the temperature is dropping, right?
Yes, because.
So do you know exactly what the temperatures was, or do you know
what the temperatures were? No, actually, I don't have that.
That's a
written
tough
down.
cookie, Kirby.
I have that for, yeah, that is a tough cookie question. You know what? I'll give that to you in another epoch, but I do not have it for the
Alright, all good. I was just wondering.
Alright. Well, alright, so here's a really interesting thing about this epoch though. For the universe to expand this fast in that little time, it had to move faster than the speed of light at that point.
Damn.
So that's.
So is this
yeah.
confirmed, or is this just like a potential theory that because I thought it was confirmed.
If you think about it, the whole big,
precedent,
what's it
but-
called? What is the Big Bang thing called? It's the Big Bang Theory. This whole
Right.
thing is
This whole
really
thing
just
is
a
theory.
theory. So everything they're looking into, I mean, there's scientists,
Yeah.
very few likely, but there's probably a few scientists who don't agree at all that the Big Bang ever happened.
Also, just
Have some
back to answer Kirby's question about the like specific temperatures. It's really hard to like pinpoint.
Yeah, I know.
Specific temperature all the
I
way
know.
back.
They have it. They have them
Just
for some. They have
so
them
for
some.
we're gonna talk about the matter era later, and there's 3 separate epochs, and I have the temperatures for those, but it's probably easier for those because it's like a set of 100,000 or a million years as opposed to like.
You know, it's really interesting that I would want to look. How do they find the temperature?
Yeah,
at
I
these
don't know.
times? I don't.
But I'm just saying it's probably easier for them to
Yeah.
find these
Yeah,
because it's
well,
like
it's later. That
way
makes
big.
sense.
It's a way bigger span of years too.
Fair.
Like if it's like a millionth of a second, like it's a lot harder
Yeah,
to find
that
out.
is-
Yeah.
It's probably just prediction technology.
Exactly. Yeah.
but, So what expanded the universe faster than the speed of light? So according to inflationary theory, there's a theory for this. Just to keep going with that, and it is distortions of space-time, which was in this case the universe's expansion. Those can move faster than the speed of light.
Okay.
So, and then, here's a little quote for this, like a real life example.
Yeah.
So the elementary particles and energy inside of the universe at that point in time is a lot like you traveling in a car, to put it into perspective. So while it's not physically for you to be able to run 100 miles an hour, when you're in the car and it's traveling at that speed, you can do so. So in that case, the particles are like you, and then the distortions in space-time are almost like the vehicle, and they can move faster than the speed of light, even though you can't. So that's kind of simplifying it, but yeah, I mean it's pretty interesting.
Yeah.
Following that one, we have the electroweak epoch, where EM and weak force split off. Electroweak because electro's EM. Oh, come on, stay locked in, boys. Come on now. But all forces had split at the end of it, and it was from 10 to the negative 36 seconds to 10 to the negative 12. So a little negative 24 difference in there. Towards the end of the epoch, they had separated, and then now you have the 4 fundamental forces. So that's kind of the main idea of this one. Strong force, weak force, EM, gravitational, they're all separate at the end of this. And now we're getting into the quark epoch. Kirby, back to that original question, what's the
Yes.
low temperature? 10 to the 16th Kelvin was the temperature.
Okay.
So
Very hot.
burning hot,
Yeah.
burning hot. Kelvin actually, do you remember the number it is away from 0?
273.
273.
Yeah.
They did that so.
It's so that there's you can never have negative Kelvin degrees.
There
Like
you
0
go.
Kelvin
That's
is
it.
absolute 0. I think that's what it's called.
Yeah.
Like the
That's
pure
the
absence of
minimum.
heat. Like you can't go below that.
Yeah. Okay. Yeah, that makes sense. So 0 is the pure absence of heat.
Yeah.
Yeah. All right. Well, in the quark epoch, all ingredients were present, but the universe was still too hot and dense to form these. But it's getting more stable, and it's cooled now. So don't worry, we've cooled it off a lot. We're now at like 10 quadrillion degrees. So don't worry about like burning your
pretty
finger.
cool,
You can probably survive that for a
Okay.
second. But quarks and anti-quarks begin to form, and here's where we can, keep getting a little into quantum physics. It gets pretty confusing. Would you guys like me? Do you think I should read a little thing about the quantum physics part about this, or not really? Do you think it's a little?
I'd be
advanced, or-
intrigued.
Yeah.
All right,
same.
I'll give it a little shot. Well, baryogenesis here theorizes that for every 1 in a billion quark anti-quark collisions, the quark was not annihilated, and this asymmetry of quarks to anti-quarks is why mass exists today. Otherwise, particles would have just collided and destroyed each other until the end of time. And baryogenesis basically caused a bunch of quarks to accumulate. So they were colliding with the quarks and anti-quarks, but there was 1 in a billion, and like they wouldn't. So that wouldn't destroy the quark, and that caused an asymmetry, and that created mass. So during the quark epoch, even though it's a little complicated, there was kind of a huge thing that was left up to chance that created all of the mass we have today. And quarks and gluons basically made a little soup, and so that has led. This is interesting. These collisions made physicists think that the universe at that time was a plasma, but it was originally thought to be gas. But because of all these quark and gluon and anti-quark collisions, that's why they think it's a plasma. So I guess that's also an insight. Here, if you guys want to pass that around, that's a little picture. You can maybe show it to the camera, but
we'll
basically what it shows is, yeah, we can pull it up maybe, but
editing.
it's just a bunch of it's like a little soup of collisions. But yeah, that's
Looks like alphabet soup to me.
a little alphabet
I'm
soup.
thinking.
That's childhood memory right there. I'll spell out my name, drink
Yeah.
it. Let's not get too into that. But yeah, quarks and gluons eventually made up protons and neutrons, and they had too much energy at that time. So then we're moving in. Next step. A few more epochs to go in this era. Don't worry, I know it's a lot. Hadron epoch, 10 to the 10 degrees Kelvin, trillion degrees. They form hadrons, so that's instead of those are made up of quarks, anti-quarks, and gluons. And then subatomic particles begin to form, and protons and neutrons, and that's protons and neutrons as the universe is cooling more. So that's a big part of that epoch. Then we got lepton, where leptons are the main dominating subatomic particle, and so after a second, many of the hadrons and antihadrons have annihilated each other. And then they create these pairs, lepton and anti-lepton pairs. And at the end, weak nuclear force and EM separate. So now we have the 4 fundamental forces fully separated by this time. I'm actually a little confused
Do you know
on...
the year?
Huh? The year?
Like how many years since the Big Bang or not?
Buddy, this is less than a second has passed.
Oh, damn.
That's why I was saying 10 to the negative 46 to 10 to the negative 32.
Right.
That's like
Yeah.
0.0001 to 0.000. It's like that.
I was saying is right when it happened.
Yeah. So, and then that was so. At the end of this epoch, protons and neutrons fuse, and they create nuclei, and that was the first element in the lepton epoch. So right at the end, that happened, and that was the end of the radiation era, and that's when we move into the matter era with different elements. The first one, helium, that was ever created. So yeah.
Yeah, so I'll take over from there because I was going to talk about the matter era. So basically, all of Alex's stuff happened like pretty quickly. You know, the matter era was kind of a bit more spread out. So there were 3 epochs instead of.
Wait, hold on. How spread out was it? Was it like we're talking like weeks, months?
Nah,
you know?
years, like a lot of years.
Okay.
It went from
all right.
50,000 years to like 3 billion years.
Okay.
So like really long
Alright,
time.
so this is
Yeah,
a
so we're
big
talking about
main
like
chunk of
maybe
the-
maybe in the middle I can pop in because I have
All of my
I have a
stuff
part
is-
that happens at 400,000 years. So.
Go for it.
Sounds good. But you go first, Kirby.
Yeah,
You said you'll
okay.
pop in the middle, buddy. If,
Alright.
you understand the English language.
Okay, so like Alex said, he ended that saying helium was the first element to be created in the universe, and then right after that, pretty much right after that, was hydrogen, which is the second one, and that's actually why those are the first 2 ones on the periodic table of the elements. So basically, the early universe was dominated by radiation, but after 50,000 years after the Big Bang, the density of radiation was passed by the density of matter, which began the matter era. So that's pretty interesting. And so it, like I said,
It is interesting, Kirby. That is.
Yeah.
Continue.
So
It's
like
interesting, actually.
it is
Yeah,
pretty
just about
interesting.
it.
So there's 3 long epochs in the.
Inject myself in there. In
Yes,
the
sir.
conversation.
There's three long epochs in the matter era, like I said. So there's the atomic epoch, the galactic epoch, and the stellar epoch. So in that order. So I'm gonna start off talking about the atomic epoch. So, like I was talking about, hydrogen was the second element to be created after helium. So this started off because electrons can attach to nuclei through recombination. So that's kind of the first thing to happen in the atomic epoch. And then matter began to dominate. Matter began to dominate over radiation. So that was the main part, because today well, today it's dark energy, but throughout the whole matter era, it was basically matter taking over radiation. So the temperature, from the beginning of the Big Bang, the temperature always has been dropping, and it dropped from, what was it, 10 to the something high,
1 million. I don't know.
Some really hot temperature, and then at the beginning of the atomic epoch, it's at 3,000 Kelvin. So that's still really, really hot, but that's not
it's not
unimaginable.
crazy levels.
Yeah,
that are,
exactly.
Yeah.
So atoms are now able to form and remain intact because of this cool down temperature. And that's not cool, but it's cooler.
Wait, you know what I would actually be interested to know? I mean, so the Big Bang, it was like an explosion, right? So I wonder, so it was very, very, very hot, quadrillions of degree, more than quadrillions
whatever
degree or Kelvin. How would a nuclear explosion at the second it explode, or the quadrillionth of a second it exploded? How hot would that be, and how would that compare?
I
would assume not
even
obviously
close.
okay. Yeah.
You're talking about the atomic bomb or something?
Yeah. So or the most powerful nuke, how hot it would.
I mean, I know that's super hot, but I don't think that's I don't think human creation can come even close to
You're
what
right.
we're
This is
what we're even
this is
imagining.
supernatural. It was God who created this. No.
It's literally
Just
God.
kidding.
Yeah.
Astrophysics right here.
Yes, sir.
We got proof
God's
of
not
it.
real. Just kidding. So and then
That's a whole other debate.
Yeah, exactly.
That might be a whole new
Yeah,
podcast.
So, Nicola, do you want to hop in? Because the atomic epoch, it ends 200 million years after the Big Bang, and now you said 400,000 years, so...
Yeah, well, anyway, the cosmic microwave background radiation
Ooh,
theory.
it's big physics theory. Right?
This is, it's one of the biggest theories.
It's a proof of the Big Bang, actually, is it not?
See, here's the thing, that's actually up for debate,
Okay.
actually, because some people believe that it is proof, and, here, let me just get into it a little bit, and I can talk more about that. So pretty much, it happened before the matter era, right? 400,000.
No, the matter era started at 50,000.
Okay, so it happened in the middle. Kind of.
Yeah.
So anyway, at the beginning, the universe was 273 million degrees, as we've talked about, in Kelvin, and actually CMB was discovered unintentionally when a radio receiver picks up uniform noise. You know when you're watching TV?
No way, it was on accident.
Yeah,
Really.
so it was. So you know when you're, it's like that. It's like when you're watching TV, right? And you're skipping through the channels, and there's that one channel with a bunch of buzz and white little dots. That is actually a byproduct of the radiation that was created during the Big Bang. So pretty much.
No way.
Yeah. So
that same radiation with the Big Bang is what makes your TV.
I'm pretty sure.
No way.
Yes,
No way, bro.
Yes. I'm pretty sure. We can fact check that.
Where's that
We'll
from?
fact check that.
Where's that from?
We'll fact check that.
Wikipedia, buddy, or what?
We'll put a fact check in the podcast.
Okay.
But anyway, it's helped us learn how the universe was formed.
All right.
So pretty much,
We got
what we can do.
over here on the side.
Hey, pay attention, boys. Pay attention. This is important stuff. This is actually shows us how the structure of the universe pans out and how it expands and how all these things actually
Hey
come into
man,
play.
I said the first part's the universe. Mine was more important, all right?
Fair, that's a fair point. However, I would argue that even modern today is the most important because think about it, we're here, and that is.
I mean, since I'm here, yeah.
Yeah. Okay. Anyway, back to business. So pretty much, by mapping the cosmic radiation, we can see the earliest stages of the universe because we can see where it was more dense and where it was less dense. So take a look at this image right here. So this is actually mapped at. This is the map of the cosmic radiation. If you want to give that to Kirby, it's another looking.
Looks like an Earth almost.
So yeah. So it's not an Earth.
Well,
But this is the universe. This is pretty much a
obviously.
density map of the universe, and it shows these areas are going to become galaxies, and the spaces in between are going to be just.
Wait, so
space.
the light areas are gonna become?
Yeah.
We can get that on this.
We're gonna have to pull that up.
Yeah, we're gonna have to pull it up. I'm not sure it's light areas, it's the dark areas, but one of the areas just expands.
Okay. And then the blank stuff's just empty space.
Yeah, exactly.
Okay.
And so that I guess we can talk a little bit more about the expansion of the universe at this point as well. So as we know, or maybe not, but the fact is, the universe is expanding. So this is kind of a complicated issue because what is the universe actually expanding into, right? Because we don't really understand how the universe would be expanding into something that is unknown, right? So what we actually can look at and conclude is that the universe is expanding within itself. So let's take a little example. So have you ever been like at your grandma's house?
I've been at my
you?
grandma's
Yeah.
house.
Yeah. So I assume they're alive.
Yeah.
Unfortunately, mine has passed.
Sorry.
Yeah.
Sorry for your loss.
Yeah. So anyway, have you ever been like baking bread, for example?
Personally not, but
Huh.
Feel like I
Anyway, you see your grandma or grandpa breaking bread, non-gender specific, and let's take that as a representation of the universe. So let's
That
now
bread is a universe?
now let's think about the universe. And now let's think we put a couple raisins on the bread. Those are acting as galaxies.
okay.
And so now as the bread expands,
Can we do a podcast just like baking that up? Just dropping it away.
the galaxies themselves don't actually expand, right? The raisins aren't changing how big and small they get. So we aren't being stretched
that's
out,
true.
but it is the time and space in between the actual galaxies or raisins in this metaphor
That gets stretched out.
that get stretched out.
Okay.
And
Yeah,
the
that
reason
makes
we can prove that is because let's make this a simple concept. So pretty much, you can determine if space is being stretched out, even if you don't know what it's being stretched out into. And this is because let's take this example. Just using simple like geometry, we know on a flat sheet of paper, when you put a triangle, the sides are going to add up to 180. Whereas on a sphere, if you have a triangle, the adds are going to all the interior angles, are going to add up to 270 on a sphere. So even if we're on the sphere,
Sorry, I'm not a geometry whiz.
even if we're on the sphere, we can still understand. So the same concept
Yeah.
applies to the universe.
Yeah.
Even though we're not looking at the universe from the outside, we still know that space-time itself is
And
stretching.
I heard that I was taught that cosmic microwave background radiation is like a proof of the Big Bang.
Yeah.
You can kind of isn't that something how related to like red shifted? You see the stars are moving away from you, and
Oh,
that
yeah,
means
we
they're
learned about that in
That
physics
means
last
it's
year.
expanding, and blue shifted means it would be
come
coming
towards you.
And it's because of the EM radiation
Yeah.
of the light, how the blue and the red is on one
So
side.
we learned that.
Do you know
Not
much
necessarily
about
about
that?
that.
Did you take physics last year?
Yeah, we didn't learn about that.
Oh, really? Who did you
Is
Physics.
take?
that physics age?
Eris.
Oh, physics H. Big
Physics
learning gap in
H.
physics H.
Maybe we
Physics
didn't learn about
regulars.
that.
So about the universe expanding, have you ever heard of anything called the Big Bounce?
I have not.
I've never
Would you
heard
like to
that.
Okay.
inform us about that?
Yeah. So basically, so you said it's kind of expanding on itself, but kind of into nothing at the same time, because we don't know what's outside.
Yeah,
the
so
universe,
I actually
right?
have some numbers as well. If you, I can get into that in a
Yeah,
little
sure.
bit.
Go.
So pretty much.
Big numbers
So
guy.
this is actually. I have a question for you. So let's take a look. So pretty much we know the universe is expanding,
Yeah.
and that means that planets, that universes are getting, galaxies. Excuse my language, are getting further and further away from our galaxy, right?
Mm-hmm.
So
Watch your language on the next one, though. Just
yeah, I'm gonna watch our language. So
watch your French, please.
So let's take a look. Do you think that space travel is going to become increasingly more difficult? Like reaching the next galaxy, do you think we need to act now in the next year?
Oh.
Because everything's moving away forward.
No.
I don't, because I think if we have the technology to leave our galaxy, which I don't even know if that will ever happen, I don't think it's gonna make as much a difference.
And see, yeah, that
Hear me out. By the time we create the technology
Exactly.
to like actually be able to improve it, that those like minor expansions, even though it
Like,
may
it
be
might
a
be,
lot of
like,
miles,
way
that
further.
wouldn't like
It's-
make
it's
the
just, like,
difference,
adds more
'cause
gas to
Our
it.
tech would have to be so advanced for that.
Exactly.
So,
Yeah.
and I'm happy to say that you guys are correct. Just separates the average
Let's
dimwit
go.
from like the scholar.
Harvard scholar, right?
Harvard scholar.
Harvard astronaut.
I would say so. I did some calculations actually. This was
There's gonna be like that one guy who would have. We need to act now, man. God.
so I did some calculations. I couldn't actually find this online, but I like did a little calculations, and
Ooh.
it's 0.88 of a light year is what the nearest galaxy is moving away from us at. And while that
Wow.
sounds like that
Perfect.
is a lot, so it's
Wow.
moving at 163,000 kilometers per second away from us, which sounds like a lot, right? But then if you think about it, it's also like 200. I'm not sure the exact numbers, but it's like it's a lot of light years away to the next universe. 0.88 of a light
Yeah,
year. It's
it's
like
not
what?
gonna-
If we had the technology to go that far, like you guys said, that 0.8 is not going to make a difference. That's per year.
Yeah.
So even 20 years down the line, that's only whatever,
Alright.
15 light years. It's really not.
Yeah.
It's nothing in the grand scheme of things.
How far
So-
light years is away is that universe? How many light
I don't know the exact. I should have put it on my sheet.
There's some galaxies that are nearby that are like not hundreds of light years
Relatively
away.
nearby.
Yeah. Anyway, continue. I actually have that in my
We'll walk
brain.
down.
I have that in my brain. I'm gonna get back to you in like 30 seconds. I have it in my brain. I didn't think about it. Continue.
Okay.
You were
So like I was
looking
saying,
for
like
that
like
comment, but-
we're gonna backtrack a little bit back to the bread example, because I know Nicola is saying it's like it's expanding to nothing, but I saw this thing online about the Big Bounce, and it's basically where the universe is expanding, so it has both sides. We know it's like some number, I don't know it off the top of my head, in diameter. So it's keeping expanding, and
Okay.
the theory is that it's gonna come like around and hit itself.
25,000
The
light years.
universe
Uh-huh.
is gonna like come around and hit itself again, and that's the theory of the Big Bounce. And I don't know if that's not confirmed or anything.
The theory?
I don't know if that's gonna
No
happen,
way.
but
That's crazy.
That's-
Is that
I don't
actually
believe
true?
that.
Where did you hear that from?
I saw
Oh,
it.
you heard that from like Wikipedia and like.
Yeah.
No, I saw
that's
on a trusted source.
You heard that from-
That is a
Trusted
Nicola source right there. I'll tell you
There's a
that.
trusted source.
Oh, but anyway, the
Nicola
closest. See, the closest galaxy is 25,000 light years away. So 0.88 of a light year.
Oh,
per
yeah,
year
you're
is
right,
like
I mean,
it's
yeah.
like
It's
what?
a sleeper.
30
Sleeper,
seconds.
Yeah,
That's a sleeper.
30 seconds, and then new like spaceship that Elon Musk is about to produce.
Oh,
out of.
God.
yeah.
That's
All right, let's get back into the
Yeah.
second epoch of the matter era. So all that Nicola talked about happened within the atomic epoch I was talking about earlier. So this ended 200 million years after the Big Bang. So after this, the galactic epoch is gonna start, and it's at the end of the atomic era. So at this point, it's cooled down even further. The exact temperature is so the atomic era is 16,000 degrees Kelvin. Galactic, it's 60 Kelvin. So that's actually whatever 60 plus 273 is. It's that degrees Celsius. So that's like it would probably get to that temperature on Earth at some point. So that's like definitely imaginable now. And hydrogen and helium, the two elements that we were talking about earlier, first two elements ever in the universe, those are going to dot the universe with atomic clouds. And there are pockets of gas that have gravity to allow atoms to collect them. And these clusters of atoms are going to become galaxies. They're going to start really small, and they're just going to keep expanding as the galactic epoch
So
continues.
just like just looking back at the Big Bang, like could we calculate how many galaxies there are potentially? Or will they keep like?
What do you mean by
multiplying
looking?
and,
What do you
like-
mean by looking back at the Big Bang?
Well, like what you just were talking about, like how the little
Start with the
yeah.
little atomic clouds.
yeah. So like if we were to potentially
Really, what?
identify how many atomic clouds there were, we
Well,
could get the
I guess
exact
there'd be
number.
so many.
Because right now what I'm aware of is that we shine a really strong telescope into the air for a really
Yeah.
microscopic part and see how many are in that one part, and then we calculate it for a whole 360
Potentially.
view. And like I don't know how accurate that really is.
Potentially, if we had the technology to do that, then I guess potentially we could figure out how many galaxies there are. But I just don't know if that's really realistic.
Yeah.
To answer your question,
How do galaxies form?
that the atomic clouds that are made of hydrogen and helium, they start off like really small and then
Okay.
expand during the
Just a
cloud.
reminder, we're about to hit in 3 minutes. We're about to hit 30 minutes. So it's like 2 minutes.
Okay. And then so this is gonna end
Can't remind us.
3 billion years after the Big Bangs. That was a really long epoch.
Camera cuts off.
And then the last one of the matter era is the stellar epoch. So this starts at 3 billion years after the Big Bang. So now that we have the galaxies, right? There's stars and stuff. So stars begin to form.
Stars and stuff. That's
Stars.
very.
Yeah, stars made out of like
That's really
hydrogen,
curvy.
helium. Yeah. And so galaxies are beginning to merge and evolve. Star formation peaks, and then dark energy begins to dominate.
Whoa.
So it went from radiation dominating during the radiation era, then matter was dominating.
Some like hellhole energy, dark energy.
Yes.
See, I would argue that dark energy still.
Yeah. I said it started to dominate.
And it still dominates
And it
today.
still dominates today. Yeah.
Okay, good.
Yeah,
Just
yeah.
making sure we're on the same page.
Yeah, of course.
I don't like to be like opening the cover of a book and we're like on different pages.
Nah, of course
We gotta
not.
be on the same page.
So, dark energy, in case you guys don't know, it's the mysterious force of the universe that causes the expansion of the universe to accelerate instead of slowing down. So the reason why that's interesting is like, Imagine.
I think once I was actually in a satanic church and I felt dark energy. Is that like the same type of like feel or what?
You know, I can't be confirmed, but
Okay. Have
No,
you
no,
have you
no,
not
no.
spent time?
No,
This is just
it's
a
not-
name.
I mean,
Have you
that's not
spent
a
time in
This
a
is just a name.
satanic
This is
church
just
or
a
what?
name.
No, I've spent time in satanic
Okay,
church, but
that's
that's
good.
different. That's different.
All right, different.
So
type
this
of-
dark energy, so like I said, yeah, it causes the expansion of the universe to keep speeding up instead of slowing down. So to put this into perspective,
I would say dark matter, you know, it's inversely related to gravity, is what the scientists have discovered. So I don't think it really has to do with like wind resistance, friction.
it's an analogy. There's no wind resistance
no way-
in the universe.
there's no
bro.
way you guys
There's no
understood that
friction in
yet.
the universe.
Yeah,
It's
yeah,
an
yeah. Understood that
analogy.
yet.
I understand.
In
Oh
this
my
case,
God,
all those
that's
things are the
crazy.
gravity.
I understand, but
Okay.
let's get like a little bit better analogy is what I'm thinking.
It was a good analogy. bro.
So what about like your spaceship flying in space? No wind resistance, no nothing, because there's no air in space.
Yeah.
Okay.
And then instead of slowing down, it speeds up. How about that? That's what I think would be a better analogy.
What is it?
I'm just trying to
Wait,
help the
okay,
viewers.
okay,
I'm
okay,
trying to
okay.
help the viewers
What
here.
is Battle of the
Okay, but I would argue that a better analogy is something you see every day.
I
Instead of a
agree,
spaceship.
I agree.
You don't see a spaceship.
You don't
every
understand
day.
how a spaceship goes through space?
No.
But what do you
I
see
don't
every day?
that
Do you see
every
yourself
day.
kicking a soccer ball, or do you see a spaceship
Alright,
flying up?
boys.
Okay, that's enough
We're
about
getting off
analogy.
Nothing about yeah.
All
Let's
right,
go back
sorry
to
about that.
let's go back to
So,
topics.
keep going with it, Kirby. Let's keep explaining
Keep going.
dark matter to us.
Okay, so and yeah, so like I was saying, dark energy. Now dark energy. So first it was radiation that dominated the universe. Then it was matter. Then in the end of the stellar epoch, dark energy started to dominate the universe.
The whole
and it
thing
is
dominated actually. It was
Huh?
like the main. It was the main
dominated.
dominant. Right?
It's pretty
It's
dominant.
like us
so
against them, Buster.
Yes, sir.
Sorry about that.
yeah. And then kept dominating, and it's actually has kept dominating until today, till this era. And there might be another thing that dominates next, but can't say that for sure.
See, I would argue that that's false actually.
It's not false,
because
bro.
I understand. I'm just looking at the word choice here. I would say dominating is a bit of a stretch, because let's take a look at the facts. Right now you're like reading off like.
What are you benching?
What?
Facts over fiction. Like, Jesus Christ.
Okay, cut that. Okay,
No, we're not.
No, we're not cutting that.
let's take a look at the actual
We're cutting.
facts.
Okay. Let me see the
Because
facts.
the fact is that as of now, the universe is moving at 73 kilometers per second.
Okay.
Oh, sorry, 73 million.
So it's expanding by that every second.
Yes. It's
Yeah.
moving. Yep. And
But what's the acceleration rate?
Dude,
and so
shut
now
up. It's like
let's go back to the very beginning of the universe. Not the very beginning, but like 400,000 years. So in the grand scheme of things, the very beginning.
Yeah.
Just like
yeah.
first, he started to grow like a tiny bit.
Yeah.
Right. So at that point, it was 67.5 million kilometers per hour.
Okay.
Second. Sorry, per second. Wait. Yeah.
Yeah.
So that's really not that big of a difference.
So you're
That
saying
doesn't-
so you're saying it hasn't really the speed at which it's expanding hasn't really accelerated. It hasn't really expanded that much.
That doesn't take away.
No,
from
the speed
Kirby's point.
hasn't really increased that much.
Yeah, he's saying that
Yeah.
the speed doesn't.
Yeah.
That doesn't take away from Kirby's
Yeah,
point that
that's
dark
fair,
matter
that's fair.
dominates because it's not like
It's
more
called
dark
the-
matter,
yeah.
automatic just increase of
That's fair.
speed.
It's called
not
the
like
dark
gasoline,
energy
like,
area.
It's like a better motor.
That's fair.
Yeah.
That's fair. Okay. That's fair.
So keep going.
And dark energy actually takes up 68% of the universe. So
Nicola, if I had to rate you on like the goofy scale of 1 to 10, I'd say like goofy from Mickey Mouse type scale.
Yeah.
But, all right.
I'd agree.
Alright,
Agree on that.
keep going.
And yeah, that's all I have on the dark energy era.
thank you for listening to our first podcast for the Impact presentation.
Yes, sir. Follow us on Twitter, Pally Impact Project, tweeting right now.
Yep.
Just finished our first podcast.
Check us out on YouTube, Instagram, TikTok, pretty much every single social media. OF, every single social media
every single
there
one.
is.
Every
Yeah.
single social media.
Catch us in the next one. Again, I'm your host, Nicolo Rafael Defenicho, surrounded by these guys, Alec
Alright,
Prophet
well, Alexander Mian Prophet.
and
Isaac
Kirby.
Ronald Keith Kirby.
Isaac Ronald Keith Kirby. Wow.
Ronald Keith.
Anyway, catch you in the next
We'll
one.
have